Antes de comenzar, permítanme leerles el disclaimer. Dice, al ingresar a la presente conferencia de la 10ª Feria Internacional, los participantes entienden y aceptan que sus datos personales e imagen podrán ser divulgados por la Universidad de Monterrey para los fines aquí descritos. La sesión será grabada y almacenada para conformar un repositorio que servirá para futura consulta y referencia a la Universidad de Monterrey y también podrá ser difundida para la misma para fines administrativos y otros relacionados con la promoción y capacitación por parte de la universidad. El acceso al material y contenido del presente evento no implica una licencia gratuita para su uso, por lo que deberán respetarse en todo momento los derechos de autor. La información compartida no podrá ser transmitida, grabada ni divulgada en ninguna forma a ningún tercero. Las opiniones expresadas en esta sesión son responsabilidad de cada participante y se solicita realizar este intercambio de ideas y opiniones con tolerancia y respeto. Buenas tardes. Let me read the introduction in English for Dr. Sikian Shen. Good afternoon to all of you. Thank you for being connected today with us. On behalf of the Universidad de Monterrey, I give you the warmest welcome to this conference that takes place within the framework of the 10th UDEM International Fair, China 2020. This time, we have the opportunity to share the topic Optimization of COVID-related operation research problems with Dr. Sikian Shen. Sikian Shen is an associate professor of industrial and operations engineering at the University of Michigan and also serves as an associate director in the Michigan Institute for Computational Discovery and Engineering. She obtained a bachelor's degree from Tsinghua University in China in 2007 and PhD from the University of Florida in 2011. Her theoretical research interests are integer programming, stochastic and robust optimization, and network optimization. Applications include optimization and risk analysis of energy, healthcare, cloud computing, and transportation systems. She is a recipient of the IIE Pritzker Doctoral Dissertation Award, first place, informs IBM Smarter Planet Innovation Faculty Award, and Department of Energy Early Career Award. Professor Shen serves on the editorial board of journals like IISE Transactions, Networks, Service Science, Informs Journal, and Computer. Her research has been supported by the United States National Science Foundation, Army Research Office, Department of Energy, Department of Transportation, and also industry funds. I leave you with Dr. Shen. Very welcome.
Thank you. Thanks for the nice introduction and an invitation. And I'm glad to, kind of see so many participants today to hear my talk about COVID problem and how do we solve, like some of those logistic problems using optimization. So thanks again. So I'm going to share my screen and you should be seeing it now. Okay. Yeah, so, okay, the link, enable media. Yes, great. Okay, great. So yeah, today my talk is about 40 to 45 minutes. And then if you have any questions, please, like ask during the talk, or, we can answer some of the questions at the end of the talk. Things are, it's not a very sort of like, strict way I would like to implement this. Just, like I would like to interact with the student as much as I can, sure. Some background about me. I'm currently an associate professor in University of Michigan. I joined the department in 2011. So I'm also currently a graduate recruitment and admission committee chair. So for some of you, if you are considering graduate school, I can talk at the end. I will show you some websites that we have for prospective graduate student, and please considering apply for either PhD or master study in our department. I got my PhD degree in Florida. I got my bachelor in China. Some of my hobbies are, like any kind of like outdoor activities, hiking, swimming, cycling. And then this is my website. So if you go to that link, you can see some of my papers and projects over there, including the talk I'm giving today. I have a PowerPoint presentation uploaded on my website. So the outline I have today is give you some, overview about different projects we have been doing since the beginning of COVID. And then, in particular on these three different topics. So I'm going to talk about COVID and mobility, how COVID affects some of the mobility patterns that we see today. And that's actually a collaborative work with one of your classmates. He was doing the sort of like a summer research at Michigan with me in the past summer. And we also have some other research related to business reopening and lockdown. And lastly, I'm going to talk more details about one project that we're working the summer about reopening the bus system in University of Michigan. Okay. So first of all, before I talk about each individual topic, this is the website that you can go to, and it's keep on being updated over time as we have more results for the project. So basically, this website gathers all the tools that we have been developing so far using optimization, data analytics, to address some of the COVID-related problems. So the three topics I was mentioning are all on this website, but you can also see here that we also have, simulation models for understanding how the virus spread in a cruise ship. We also study some other things on this website, okay? And this is my team. So we have graduate students in University of Michigan. These are PhD students I have working on different problems over the summer, as well as undergraduate student from University of Michigan, as well as two of them from your university, University of Monterrey, to work on different things that I have related to COVID, sort of like how to solve COVID and address some of the issues. And again, I thank all these wonderful students who work very hard to solve the problems that we see right now. Okay. So before I start, I would like to, give you some overview about the general approach that I view can be helpful. Most of the studies that you see are probably, predictive models, right? So this is what data analytics can show us. For example, if you want to see, what's the trending of the infections in different countries, you go to this website, our wording data, they have a lot of charts you can, output, okay? But then basically what these charts do is they do not give decisions like what you should do, but instead they will tell you, what has been, observed, right? And then they can help you make some predictions. So then, what I care more is sort of like, in addition to data and prediction, can we transform them into action and solution? And this is what operations research sort of like mainly is about, in my opinion, as different from, machine learning and some statistical learning approaches, okay? So we talk about flattening curve, how to do it, how to, solve problems encountered in epidemic prevention, intervention, control, and also after the pandemic, how we recover, right? There are a lot of decision-making models that you have to deal with. And those are mainly coming from optimization, system engineering. So what the major of industrial engineering is mainly doing, I think it's in this domain area, okay? So back in March, in fact, I wrote a sort of like a summary, and which is more like a literature review type of document about, here now we see COVID has been spread out all over the world in March, right? And then what different countries can do to solve the problems. These are not my research, it's just like, things are already being in literature, which I think can be, helpful in terms of solving supply chain problems, kind of a delivery problem and so on and so forth. I put them together and put on my website about, sort of like this literature review summary. And then we implement some of these models to solve some problems. And the first project is related to, like, how do you build a data dashboard to view how COVID-19 affect people's travel behavior? So if you think about the relations between pandemic and the mobility, you can, some of the literature, you can think about, because of the infection, then people may not be willing to travel, right? So there's a lot of literature recently came out studying people's behavior and mobility pattern change in some major countries, major cities, right? Depending on their COVID-19 infection severity, okay? So these are some papers we find. And also on the other hand, because, people's behavior change or, you can intentionally change their behavior, in fact, by designing your mobility system differently. And we're going to show you one of the example at the very end about this, school bus system that we designed for University of Michigan. So you can do the other way around, which is by changing mobility, you can change the infection, right? Hopefully, in the right way, okay? So then, there are studies about, what if these mobility patterns change and then, people less travel, how that is going to control the virus spread. And then they do some real data study in China. And also they study, different models that can be utilized in different countries, different regions, and so on and so forth, okay? And then we also find papers that try to bridge the two. So they have an interactive platform that, if there is infection increase, and then you will see some travel behavior change. And then because of that, then the infection will go down or up accordingly, okay? So that's a literature review. And, I work with Huan, who is working with me in the summer for the summer research project. And we're basically looking at our, the data source from Google Community Report. And then, they show, you can pick the country, you can pick what kind of, like a travel activities, it's work related, it's retailer travel, it is, grocery shopping or whatever, right? So then they will tell you what these travels are about. And you can try to look at, how the patterns that people have according to the pandemic situation in those regions. So we use a time series decomposition model to see what is the trend component, what's the seasonality component, and what's the irregulation component. And you can use Python to sort of like graphically show the prediction of the travel. And these are some snapshot of the data dashboard that we can use to see how the mobility are correlated with the infection. And these are all available on the website that I just showed you. So in order to find the website, you can just like Google optimization data analytics for COVID, it should show up. You can also go to my web homepage, and it's on the homepage. The link is on the homepage. So you can pick like you want to see, different states in United States, or you want to see like different country in the world. You can also see, mobility behavior depending on sort of like, how they are related to the infected cases and so on and so forth. Again, as I said here, these data dashboards are not decision-making, right? They're just sort of like you have the data, you try to do some observation, some prediction, you can use this. We also show you, sort of like how mobility changes in travel to grocery, pharmacy, which are sort of like necessary travels people have to do, and to workplace, and so on and so forth. Some of the statistics, we did some analysis in terms of people's sort of like pre-lockdown versus post-lockdown change in terms of how often they travel to different places. And you can see a big difference in terms of the policy, right? Because of the state in place order, then people intend to have a significant change in terms of where they go. So these are all sort of like the statistics that we can find from the mobility data that I show you. You can go to the Google site and find the mobility data, how we can use them. One way is doing this. Okay. And the next one I want to show you is related to our decision making. Okay. So it doesn't say that, like with these mobility data I just show you, you can't do any decision. In fact, the next step would be, these are the, the analysis, the data, you can implement them into some models, and you can sort of like solve them to find the best lockdown decisions and so on and so forth, right? The other thing that we can do is to look at relationship between different business and do a, sort of like a decision. So the first one I would like to introduce you is this paper that we did for like deciding how to select facilities to close and what population we need to get vaccinated under a, kind of like a disease outbreak. So this was a paper that I've done quite a few years ago, in fact, in 2013. And then we look at some disease that is vaccinatable, right? So you have the vaccine, but then now there is an outbreak. What kind of decisions government can do? In general, there are two types of decisions. First, lockdown. Second, vaccinate, right? Vaccinate subgroups of people so that the disease can be controlled. So then the question is, how do you do that? Well, there's something called integer programming that you can formulate. And this integer programming, you have binary variables saying which facility I would like to close, which group of population, depending on their age, depending on how easy they get infected, depending on how mobile they are, and so on and so forth. You can vaccinate them. And then there's certain budget that you can lock down and vaccinate. So these are sort of like knapsack constraints that people often use in integer programming. The difficulty part is solving this problem with nonlinear objective functions. Because, depending on the lockdown facility, then people are going to change their behavior. Like say, oh, this facility closed, then I go to visit somewhere else, right? And then, like some people are more contagious because they haven't been vaccinated and so on and so forth. So then you have all these parameters play a role in terms of how many infections you're going to get depending on the decision you make, which is Z and X. And these turns out to be nonlinear, which is exactly speaking, they're bilinear. You have the Z times X, right? And so how do you solve the knapsack problem with bilinear objective? This is what we mainly did in that paper. I just want to bring up to you that, you can look at a static model to solve a lockdown problem. And then, like if you zoom in this problem a little bit, think about the problem. I would like to build a quarantine model, right? Which is, I can view my whole, kind of like region as a network. And this network has different nodes, and each of the nodes represents some sort of like a population groups, right? They interact with the other population groups. You also have facilities, which, you can be one of the node as well. The population group will visit those facilities. And then what you need to decide is to find the most critical node, right? And you block them. You say, okay, I'll close down this facility, I'll quarantine these people so that you will stop the virus spread. So one of the models you can look at is this interdiction model for disconnecting a network. So if you look at your network, and then basically you want to identify some critical nodes and you block them. And by blocking them, you'll delete all the arcs that connect to this node. And then the objective is to say, you choose some node to delete so that my overall graph is disconnected as possible. Okay, so in the network optimization, basically you can have different ways to define how disconnected a network is. And one way is to say how many components you have after you delete a certain node. So what does a component mean? A component is a subgraph that is connected, okay? The maximal connected subgraph, basically. So in this picture, if I ask you to delete one node such that it will get disconnected as much as possible, if you follow a greedy algorithm, right, you will identify this gray node. And in fact, because that has the most number of connections. But if you delete that node, in fact, you'll realize that every other node is still connected. You still have one component, right? So the greedy algorithm is not necessarily producing you the correct answer. So then you should build a optimization model to say, I'm deleting some of the nodes. You have some variables to tell you which node to delete. You can only delete one node. In this case, capital B equal to 1. And then after deleting it, you identify how many connected components you have. So the optimal solution produced by the model is in fact this black node, by deleting which you have 1, 2, 3 component up here, and also a big component down here, okay? So this is basically some work that we have done in the past to say, how would you build a model such that you can identify the most critical node to block a network? And this kind of model can be utilized for lockdown as well. And then in the summer, we did some sort of like easy way of looking at a reopening problem. So let's say I lock down some business, and then you can also reopen some of those, right? So basically, if you think about reopen a business or reopen a state, what you have is their risk index, their economy benefit, and then their employment contribution. So by blocking some of the, by deleting some of the state, right? So then you will achieve some risk level, some economy benefit, some employment benefit. And then what you can do is building a knapsack model with one being the objective. I say I want to minimize the risk while maximize the benefit I have. And you can give yourself a certain budget, say, like how much risk you can tolerate, and you want to maximize the economy, and so on and so forth. So these knapsack model can produce you some preliminary results for reopening. But if you look at, this way of doing the business, if you open some state, it doesn't necessarily say that it's going to work, because some other state need to be open at the same time if these two state trades, right? So if you look at, considering the business trading across different states, different countries, this is what picture shows the trading with the United States in the world. So it's like across different countries. The US doesn't only do business with itself, right? So there is a lot of, kind of like trading you have to look at. Then, by having the right revenue calculation, you have to have all of the partners states or partner countries reopen as well. Okay, so this is why we get more interested in looking at a more complex network-based model for this reopening process, where you look at regions and then you look at industries in different regions, and you have like different time horizons that you can make the reopening decision. And so you can see that the decision we're making has reopening or close down. We have also amount of business trading that is in between different regions. We also have local trading, right? And then eventually we're tracking, because of these reopening decisions, how many infections I'm going to see in the next periods, right? So then you can build a big integer programming model where each of the constraints will say, oh, I would like to, if you do not reopen, then you cannot do trading. Unless you reopen two states together, then these two states can trade. Okay, so there are a lot of like models that are constraints we can build in order to describe the right decisions to make. And then the objective is maximizing the revenue or the economy benefit, and also minimizing the infection. Okay. So then we did some sort of like a computational result test using the data in California to see if, I see these infections in California, then what would be the right decision to do regarding each type of business in California. Okay. So that's sort of like some integer programming you can do for reopen and lockdown. Last part I would like to talk about is this public transit system redesign. Okay. So this project comes from a project I was involved in University of Michigan regarding how we can, reopen the campus in fall semester, and how do we run the buses so that we still ensure that it's a safe public transit system in campus. And we have 4 campuses in University of Michigan. And so I'm going to show a short video that records our work. So I collaborate with some other teams who does the study of, simulating the aerosol particles in the bus if someone sneezes, and see how that goes. And then, we can talk about the models we use.
What we've been doing is generating aerosols inside the bus and watching how that aerosol is transported.
Aerosols are liquid droplets in air that can be potential conduits for the coronavirus. The team of Michigan engineering researchers are measuring and modeling the concentration and dispersion of aerosols in buses in order to learn how to better filter them and keep users safe.
So we sampled at the driver location, at different passenger locations, and studied the time response to see that aerosol, and how low would the concentration go if the windows were open or other vents were open versus a closed bus with just recirculating air after air conditioning.
By collecting data in a variety of situations, researchers are then able to create models that show the likelihood of coronavirus transmission with a variety of variables such as rider capacity, ventilation rate, and mass usage.
Our model tells us if you have a sick person on the bus and the bus is full, how many people got sick in a 15-minute bus ride.
Researchers then took the data and fed it into a mathematical model that creates optimal routes and user capacities for a variety of scenarios.
We put all these objectives related to the bus operation, related to the passenger experience in a single objective function. Then we build a simulation model to try to simulate all kinds of possible demand scenarios and to see whether or not these routes are resilient and also robust.
From this work, university officials have built specific health measures for a variety of situations to keep both riders and drivers safe.
The changes in a nutshell are duration of trip, number of people on a bus, wearing masks, and dealing with the fact that we're going to keep the windows open. It's going to be a little bit different.
This will be a finite period of time. This will not go on forever. We want to get back to some part of normalcy, but we need to do that safely.
Okay, so yeah, basically what I wanted to show you is the outcome, and how we did this redesign basically follows the following. Okay, so in transportation, you know, this hub and spoke design is being there for a long time, right? And then the reason of that is because, you know, it can be more efficient to transport people, especially in large cities. So if you look at the Michigan's, you know, kind of like old bus system, we have lots of long routes. And as I mentioned, we have 4 different campuses. So the North Campus is like here, where I work, you know, College of Engineering is in North Campus. And then we have like a medical campus and central campus, and then, you know, South Campus. So we're South Campus and mostly aesthetic, you know, kind of like facilities. So you have like gyms and everything in South Campus. College of Engineering North Campus, there's some graduate student living North Campus. And then we have also Central Campus as our main campus, which has lots of departments like pedestrian, like shops, and also restaurants, student housing, a lot of them in Central Campus. So if you think about driving from North Campus to South Campus, it's about 20 minutes, I would say 20 minutes driving distance if you drive a car. But if you think about bus, right, they have different stops, and each of the route here is about, I would say 20 stops. And so even without the stops, going all the routes from North Campus to Central Campus, and there are several of them, in fact, also from east to the west, each of them is about 40 minutes, 45 to 50 minutes. And then you plus the stopping time is, you know, easily go over 1 hour. And as you see in the video, we want less than 15 minutes, right, for each of the route we have. So how do you make sure that you can have a design that holds the same amount of people, but then, you know, can run more efficient? And the hub and spoke is normally that answer, which is you will identify some hubs, and those hubs are the most frequently used bus stops. And then you will have very frequent connectors between the hubs. So in this case, I have 1 hub in North Campus, 1 hub in the Center Medical Campus, and 1 hub in the Central Campus. And then just like run bus between these 3 hubs very frequently. And then, you know, like people are going to other places in North Campus, then either they can walk there or they take another small routes, right? And so that's a spoke. So this is the idea, but then which stops we need to use as hubs and which stop we need to include into the routes are what the optimization model needs to do, okay? So we collect data to use, which is the current data, which is how many existing bus stops we have. There's 110 number of existing bus stops, 7 different campus routes, 5 different medical focus routes, and so on and so forth. And we also see how many buses we have, what type of buses they are, what's the capacity we have, and how many drivers we have. And we have 3 different working shifts. With all these data, I also need to understand how frequent each location people use the bus, right? So to do that, I need to understand where people live, what their course schedule looks like, and so on and so forth. So we get a lot of data in Michigan from different parts of the university. And we build this integer programming model to say which stop I need to be make as a bus stop. And for those that are not bus stop, we need to make sure the ones that we pick can cover them, right? Meaning that if I have a demand in those locations that is not picked by my model, then someone there should be able to walk to the selected bus stop within 5 minutes, okay? And I also need to make sure once I connect these bus stops that I pick, the routes needs to be less than 15 minutes, all the routes, okay? And I need to have enough number of buses covering them and so on and so forth. So I put all them in one of the model, and then the model will produce me something like this. Okay, so they say that, okay, pick Pierpont, pick, there's a medical one and there's one in the Central Campus. So pick these 3 of these, and then we connect 3 of them by main commute. Later on, we need to decide how frequent this main commute needs to be. But now I just have the routes, right? And then I also will have 3 routes in North Campus, 2 routes in Central Campus. And the point here is that all of them is less than or equal to 15 minutes drive, even including the stopping time. And then we also, the next step is to see how many buses we need to use on each of the route, okay? As you see in the video, we also need to make sure we don't use all the seats, because then if someone gets sick, there are a lot of people in the bus will get sick. So we need social distancing in the bus. And to do that, we need to say, okay, even we use the number of buses on each of the route, but then we can only use like 50% of capacity. So each bus can hold 78 people, and we can only use 40 or less seats in each of the bus. And then even the university want us to use like less than 25 capacity, and can we still do that? Okay, so we try to match the peak hour demand that we had in the old bus system by using a new bus system. And this is like a table that we show you that yes, we can do it, because if you consider the current system or the old bus system, the frequency that goes through some of these, kind of like hubs every 2 minutes, and then using the calculation, we know that the capacity we have is holding to around 2,000 people per hour, okay? If we're assuming every bus is full, running for an hour. In using our system, we make it more frequent, so we can actually do 1.1 minute frequency, and we only use half of the seats, and we're able to do a capacity this. So, and the number of buses we're going to put on the main commute is 20 buses. So, we do that for every single routes, and then we make sure that we don't need to add new buses. And I do get one, it may not be a question. I don't understand Spanish, sorry. Yeah, it's probably not a question. All right. So then, like now we have the design, right? We have the routes, we have how many buses we would like to put in each of the routes. How can we make sure that our system doesn't go, crazy if in some situations that been never encountered before? So we use a simulation model, and we set up all these, kind of like data using the simulation model. And basically we put all these, kind of like a travel time in between the bus stops that we pick, and then also some waiting time based on whether this bus stop is a busy bus stop or not. If it's busy, we assume that each bus will stop there for 2 minutes and then going. If it's not busy, then only stop there 1 minute, okay? So we put a lot of data in the simulation model. What we care about is 2 types of measures, right? One is how good our system is. Is bus operating well? Can we still hold the same number of people in a peak hour as before, and so on and so forth? What's the bus utilization rate, right? The other thing is related to passengers. So as I mentioned, if you break down long routes into this hub and spoke design, right? And because you do that, it's highly likely that somebody who could take one bus now has to go several transit. Is it going to be happening? Right? So, and how frequent this will happen. So we need to report the passenger waiting time, riding time, and walking, because we say that, for some passengers, if you can walk to a nearby bus stop within 5 minutes, we'll let you work instead of letting you to ride a bus, right? So, do they walk more? How more they walk, right? And so on and so forth. So we did analysis of these 2 different things. We run the buses, and as you can see here, because this route is pretty busy, we put a lot of buses on the main commute. So a lot of people can go from North Campus to Central Campus very easily right now, as compared to before they have to wait for long bus, okay? And then, within each campus, a lot of them actually will walk because it's not really far, okay? And then some of them, they live pretty far, then they will take a bus, but those buses are more frequent than what we have right now also. So as you can see, most of the bus is within 15 minutes, and actually it's only 11 minutes. And then, we're solving that problem. We also report the bus utilization rate using simulation. Then we see that the North 2 is the busiest route. So that helps, because later, if you know that there is some bus breakdown in North 2, we can move some buses from less frequent used bus route to North 2, okay? We see that main and North 3 has high utilization rate, And Central 1 has the least utilization. So we can move some of the buses from Central 1 to North 2, for example. Okay. And then, you know, we also have passenger waiting time, transition time. And then most of the passenger, right, more than 35% of the passenger, in fact, wait less than 1 minute because we have so frequent buses now. And then the reduction of the bus capacity has no significant impact. If we take one bus from each of the route, in fact, it doesn't impact our results that much, just again, because we have very frequent buses now. 70% of passengers only take one single bus and only 30 of them will make transit, okay? So still, you know, a lot of people are commuting between the hubs. That says, right? On average, people will take 1.3 buses to complete their trips. And as you can see, we do some random bus breakdown on each of the route, and then this will show you how big impact that will be. And again, you know, like waiting more than 5 minutes is what we consider as significant waiting, and we don't have that many people waiting longer than 5 minutes. Okay, so less than like 30%. So using simulation and optimization, as you can see, we can really solve this, you know, like public transit redesign problem. And as a conclusion, I just want to say basically, you know, like, I think it's very important to not only see the data, but also try to make decisions and action using the data. And this I gave this talk when I had the first summary, in fact, back in March in several occasions. And this is exactly the last slides I showed them. So back in March, right, as you can see here, this is a tweet account from WHO. It basically says that, you know, it took 67 days from the first reported case to reach the first 100K case. But then, you know, 11 days for the second 100K case shows up, 4 days for the third 100K case shows up. And I think, you know, like for a lot of countries these days, only 1 day it can easily reach 100K case. And that was back in March, right? As well, this was, I gave this talk, as I was saying, you know, in April, and that was the data I showed them. It was pretty bad already in April, feels like. There's a 1 million infected cases and 55,000 death cases from the US. But now if you look at now, you know, it's much, much worse, right? So what people can do, right? Try to do more quarantine, lockdown, do scientific way of controlling the disease, try to increase the testing ability and try to, you know, avoid medical shortage, right, supply shortage, and avoid exceeding healthcare capacity. Try to triage patients, do not let them jam to the hospital all the same time. And also limiting travel, right? All these can be done and can be done scientifically using optimization models. So this is what I have for today. I can take any questions you have. Thank you.
Thank you, Dr. Chen. I have several questions here. Yes. Okay. At this point, we'll start with the question and answer sessions. As I already told you, we have as attendance UDEM students for industrial and mechatronics engineering programs. I will ask you to raise your hand or ask your question by the chat, or if you want to make the questions personally, you just can ask for the permission to enable to speak. So this is time to questions. There's a comment here from Diego Parras. It says, so many factors to take into consideration. Impressive, congratulations. And the other chats were about the registration, so don't worry about the first chats that appeared in the middle of your session. So this is time for questions. Sorry?
Sorry, there's one in Q&A. I can try to answer first, maybe.
Sure.
Yeah, so it says, which programming language do you consider is the most useful in big scale data analytics investigation? So the programming language depends on what you use it for. If you say, okay, I want to do some statistical analysis, R is pretty popular. So, you know, and I know that Python has been developing a lot of packages for statistical analysis. for solving the models, I was just showing you, right? Optimization model, you need to make decisions like binary decisions, X is either 1 or 0, that kind of thing. I recommend people use Groby. So it was Cplex before, but then the group of people who created Cplex sold Cplex to IBM, and then they created Groby now. And actually, I can show you pretty quickly where to find the documentation. So share screen, sorry. Groby, yeah, so this is the programming language I was talking about. Solving integer programming, no doubt, I think you can use that pretty easily. And the one thing good about it is they give free, they gave free software. It's not like a trial version to anybody who has a .edu account. So if you use .edu account to sign up, then you can get the software for free. And they have a lot of resource here that you can see their code examples, right? What kind of problems you can build using Groby and so on and so forth. And the code is super easy. So it depends on, you use Python, you use some other language, they all can, kind of interact with the language you're using. So for the solver, I would definitely recommend Groby. The next question is, when do you did the vaccine and epidemic model? Was it for something you were expecting in the future? So basically all the models that, we build and submit for publication, I would say maybe 90% of the papers that you read is generic models, right? So basically, we say, if you have some epidemic or, the pandemic or outbreak, it could be even like just flu, right? Influenza. Suppose that you have vaccine, right? Versus you don't have vaccine, right? If you don't have vaccine, which we have, it's a situation for COVID right now, you can only lock down, which is okay. You can still use that model. You just make all the decisions related to vaccine disappear from that model. Okay. So yeah, so definitely there's has been pandemic in the past. It has been, it will be in the future. So if you write a model, you say, oh, this is a scenario I'm thinking about. And then I would like to, propose a method that people can use to solve that problem. But of course, you need to say what assumptions do you make, what kind of data you need to solve the problem, and so on and so forth. Then, people can use your code pretty easily for some specific things they're doing. Okay. Any other questions?
I have one. About your project of reopening the states and the economics in the states, and have you considered to reclose once you reopen, maybe given the waves?
Yeah.
Close.
So that's a good question. Actually, our model can deal with reopen and close. You just need to, allow your X to be sometimes 1, sometimes 0. But if you say once you reopen, you cannot close, then you just need to add one more constraint, says once X is 1, it will be 1 for the rest of the time period. So yes, the model can deal with both. It just in reality, how quickly you can close once you reopen, right? So you may want to have some practical constraints. Say, if you reopen, you have to reopen at least for 1 month.
Yeah. Okay.
Otherwise, you will just back and forth and confuse the people. Yeah.
Have you had the opportunity to present these models to somebody in the government or
yeah, so I have been presenting this several times in some government, kind of like gathering, but it's not like to the US government. I think at this point, I don't think they're interested. The current government, they are not doing anything centralized to control the virus. So yeah, we just hope that, people can get more.
Here. Okay, thanks. We have another 2 questions.
Is there a chance that the new bus routes you are working on will become permanent? It seems to be overall super, even when the capacity of the buses is limited. So that's a very good question. In fact, I think so, because the university always want to implement something more efficient. But the downside of those systems, right, if you think about hub and spoke, for example, in big cities, you can never do very long routes. You have to do hub and spoke, but then that means that people have to take transit. They have to take a bus to some subway station, take a bus to subway station, then, take a bus or walk again to where they walk, right? So I think with the university the same. I discussed with the, the campus translation department who asked us to do this. They in fact want to do happen so long time ago. It's just like they're afraid that the student doesn't want to walk like 5 minutes. A lot of students here doesn't want to walk at all. Now, like the pandemic becomes a good opportunity. So then, once you have that system for a while, probably people get used to it, and we really hope it can be permanent, because the efficiency is just like much higher as compared to the old system. And then, so the other question will be, do you go to the government and propose these models? So a lot of my colleagues, as far as I know in epidemiology, have done that with the government, right? So that's why I say at the very beginning that, maybe, the data models, right? The prediction models are more aware to government agencies and also to the public, because, that's the first thing you can do. Once you have the data, you can look at the trend and you see how, how this pandemic is going and so on and so forth. The decision model is less aware to a lot of people. And that's sort of like our goal, to try to publicize it more. So as I said, I gave this talk a lot of times in different occasions. Some of the audience are from the government, but not like directly to the government. I talk about this in a lot of like data symposium in Michigan, in the US. So, hopefully, at some point there will be more people willing to use scientific ways of solving this pandemic issues. Okay. And if you go to the website, I show you some of the link before actually. If you go to my website, so this is a link I was showing you that you can find all these models. We actually have worked on each of the models, just that depending on what I have time, some of the models will show you we got some results like this bus model. We put our results here so you can read a little bit more detail. But then some of the models like this, for example, prisoner release problem, if you have an outbreak in the prison, right? And then for some of the prisoners, you may consider early release, who should be early released to fight the outbreak and so on and so forth. We have some Markov decision models as well, but then I don't have time to put in the website yet. But you can see that there's a lot of problems here, right? So some of the problems is like government problems. So the audience should be the government, like, how do you locate for testing facilities and so on and so forth? How do you reopen business, right? Some of the problem like bus design, that's the University of Michigan is the audience. Some of the problem is like dispatch and delivery. We did some of those. Then those are, kind of like companies who is running restaurants, right? How should they deliver food to their customers, given that everyone wants to do food delivery now? Can they afford it? So there is a lot of like things that, and this work is done by one of the student in your university again. He joined us for the summer research. So then the question is, you have the choice of working with these, platforms like Uber Eats, that, DoorDash, versus you can deliver by yourself. Which one you would like to pick, right? So there's a lot of interesting problems here, but the audience will be different depending on what problems you're solving. And I think we have do we have chat questions?
Chat questions. Let me see. Yes, there's one. It says, can you read it?
Yeah, so, but, when I was doing this in March in Mexico, they was just starting, right, with the COVID and quarantine. Is there a way a country without information of its own country because of the situation hadn't gone out of control, there can make an optimization model for their own countries, taking consideration prediction of the economy? Yes, so basically, like these models, right, I was putting here, they relate to different phase of the pandemic as well. So, like testing models we're doing, actually, I didn't have the details here, but we are close to finishing up a paper and I can put that here soon. So the testing problem is, it has different phases. So at the very beginning, right, when the testing kits is not enough, how do you allocating the testing? And then now it's like, I think a lot of countries has all these testing available. It's just like, who want to test? So all these different problems are associated with different levels as well, depending on the data input you put. And that's a good question. Like when I was doing this in the March, in fact, we have nothing I'm showing you here now. The talk I was giving in March is a different talk, which is this guy here. In fact, let me find my website. Yeah. So the talk I gave in March was a different talk, which is a summary of the operations research and industrial engineering tools. Okay. And then there was, I think, my department recorded actually. So this is a talk I gave in March. It just like talks about, oh, you know, people have been doing a lot of like problem solving in the airline industry. And now you see the airline gets dropped, right? You know, how we should prepare for that and so on and so forth. So I think, you know, these models, the useness of those is that the model is there no matter what, and you can input different data. You can data from a country that has very bad infection. You can also input the data from a country that has very small infection, and the result will tell you what to do. Okay. And of course, you know, the other way you can do this is looking at the countries has been through the process, right? So I keep on, you know, saying in my talk, I hope, you know, government in the US can find a way to do a centralized, you know, control of the disease. I mean, just looking at, you know, how many phases that China has been through. And now China is in the phase that it's now almost clean, but it has like, you know, flights coming from different countries, and then what they should do in order to, you know, kind of like track people once they find there is an infection. So some countries are in the phase of, you know, kind of like later phase, some country are in the earlier phase, and you can learn always from a country that has been through this. So, yeah.
Okay, I think there's no more questions. Let me share my screen a little bit. Kenya, can you allow me to share the screen? It says I can't. Okay, here it is. Okay. Dr. Shen, on behalf of the Universidad de Monterrey, we thank you for this contribution in this matter to help us to know a little bit more about your work. And I personally thank you for agreeing to offer this conference. A continuación en Spanish, les agradezco a todos los alumnos que pertenecen a la Universidad de Monterrey que no olviden registrar su asistencia, por favor, y les va a llegar un link con una evaluación de la conferencia para que también, por favor, la llenen. Dr. Shen, this is a visual acknowledgement for your participation. I will send you as soon as we finish this session. Thank you very much for your
Thank you. Thanks a lot for having me here today.
Thank you. Very, very interesting your work. Thank you.
Yeah, thank everyone for attending. Appreciate your attention. Bye.
Bye-bye. Thank you.